we're going to be looking at this differential equation modeled in a real world scenario. So what we're looking at is the growth of a tree, and that's represented by this formula, dh by dt, which is the rate of change of height with respect to time, is equal to 3 minus the height divided by 10. And we're going to use this differential equation to learn some things about the growth of this particular tree. When dh by dt is equal to 0, we have h is equal to 30, and dh by dt being equal to 0 means the rate of change of height of the tree is 0, so the tree's not growing anymore. And if the tree's not growing anymore, then h is equal to 30 meters must be the maximum height of the tree, right? Now, the next thing we're going to do is we're going to find an explicit formula for h in terms of t. So the way we're going to use that is using our techniques of solving separable differential equations. So I'm going to multiply both sides by 10 dh by dt is equal to 30 minus h. And I'm going to divide by 30 minus h and divide by 10. So, and then bring up this dt and integrate both sides. So I'm going to get the integral of 1 over 30 minus h with respect to h over the integral of 0.1 with respect to t. And now, if you do need to see any of these techniques for the separable differential equations, then there will be a card up here. For the last video we did some examples explaining this a little bit more in depth, but this integrates to minus ln the modulus of 30 minus h, and this is equal to 0.1 t plus c. But the trick is here is that, well, we already worked out that the maximum height of the tree is h, so we don't need this modulus sign anymore. So we actually have minus ln just 30 minus h is equal to 0.1 t plus c. If we think about tree growth, this model comes in when the time t equals 0, and when you first plant a seed for a tree, the height is equal to 0, alright? So, using these boundary conditions, substituting in 0 as t, t is 0 and h is 0, we get minus ln 30 is equal to c. So, c is equal to minus ln 30, right? Now we want to solve for h. So what we're gonna do is get all these ln terms onto side, and rearranging the equation gives us that ln 30 minus h over 30, using our laws of logs. You see, if we add this to both sides, then we got ln 30 minus h minus ln 30, so you can combine those, and that gives you ln 30 minus h over 30, and then subtracting 0.1 t from both sides gives us minus 0.1 t on this side. Then we want to take exponentials on both sides, so that gives us 30 minus h, and then would be over 30, but we're going to multiply it by 30 as well in this step, so that gives us 30 e to to the minus 0.1 t there. Alright. And now solving for h, we're going to add h to both sides minus this from both sides. And then factorise out the 30. So that gives us h is equal to 30. 1 minus e to the minus 0.1 t. Okay, so now we have h in terms of time. So if we want to say how big is the tree going to be after 2 years, we can put t equal to 2, right? Or, well, no, 4 years, t equal to 4, you know, so we can do all this stuff. And the other thing we can do is we can say, well, how, we know what the maximum height is, 30 meters, but how long is it going to take to get to the maximum height? So we put in h equal to 30, and then we solve for t. Alright, so you can see you can learn lots of things from these differential equations. You want to be able to get manipulating these, and the real challenge as you progress through math, and if you're interested in doing this sort of modelling, is forming these equations. And you know, often they're a lot more complicated than this, and as you get higher up in math, you have to use more, you know, analytical approaches, or at least more sophisticated ways of solving these equations. You know, not everything in the real world boils down to a separable differential equation, but this is a relatively suitable model for tree growth. And you can model loads of things, populations. I'd say you drop a bit of oil on the floor. You want to see how the radius of that oil drop expands over time. You can model that. Pretty much anything that requires a time component can be modelled as a differential equation, but there's loads of things you can even model in terms of lots of other stuff, and maybe we'll do more examples of all these in future. But for now, that's it for this video. If it was helpful, please like and subscribe, and I hope to see you in the next one.